Hello, everyone, and welcome to this panel discussion on towards regional high resolution weather forecasting with machine learning, which is part of Module 8 in this training series of Course 2, and which is on architectures, data, and prediction. Today, we are going to discuss some of the emerging themes that are coming out for using these MLWP architectures for high-resolution regional weather forecasting. And the themes that you see in front of your screen are, for example, like what are the different pathways? So in the literature, or even in like pseudo-operational modes, what we find right now in different Met agencies are choosing different models. For example, the limited area model, the stretch grid, or downscaling approaches. So, and then we will talk a bit about like what are the challenges in training at such a high resolution from a data perspective, from a computational perspective, also touching upon the architectural details. And then we will, of course, discuss about the verification part, how to trust these forecasts, and what are the difficulties, or I would say the challenges are there for operational integration. And then we will talk about forecast in a box, which you will know about it in a bit after some time. And it's a local model, and about its usefulness and what is it and how is it portable and adaptable to local user needs. Next slide, please. And to have this discussion, we have experts from different Met agencies with us, and also researchers. As you see in front of your screen are Harvard from Met Norway, Joel from ETH Zurich, Roland Potast from DWD, and he's also part of University of Reading. And then we have Leila from Finnish Meteorological Institute, and Corentin from ECMWF, and myself, Vartan Chatterjee from KIT as the session moderator. And just to give you a brief about today's program, after this, we will have the opening statement by the experts, and then we will have a moderated discussion based on the themes, which you will see. And then we will have questions from the audience. And this, of course, as you might know from previous experiences, that we have many questions. And of course, we will try to cover as many of them, but this will be based on voting. So in your chat button, you will find like if somebody has asked a question, you can upvote it so that we can include it on a priority basis to ask it here. Otherwise, we will try to answer them later on in the MOOC platform. And afterwards, we will have short reflections, and that will be the end of the panel. And yeah, I think now we can start by opening statements from the experts. Let's start with Howard.
Yes, thanks. Hello, everyone. My name is Håvard Haugen, and I work as a researcher at the Meteorological Institute in Norway. I have a background in physics, a PhD, and I've worked now at Met Norway for roughly 2.5 years, developing our machine learning weather forecasting model called Bris as part of as a larger team. So Bris is a stretched grid graph neural network model. And what stretch grid means is that we run the model as a global model, similar to the AIFS, but we have increased resolution over a limited area of interest. So the Nordics, in our case. This is, of course, inspired by the traditional NWP LAM approach, but instead of having a forcing global model that you fetch the forecast from, we run both the global and the limited area forecasts together seamlessly in one model, where where information can propagate between the two domains seamlessly without any and of course this is enabled by the fact that machine learning models are so quick compared to NWP models. We're actually able to run these large models. Bris is trained to be a probabilistic ensemble model using the score-based CRPS approach, also similar to AIFS, and we've also experimented with adding these sort of spectral terms to try and improve the spatial coherence because we see that this is a problem on the sort of smaller spatial scales, typically 2.5 kilometers that we have in our regional domain. Just finally, this model is now running pre-operationally at Met Norway, and it has for roughly half a year. So we can now generate a 5-day forecast with 16 ensemble members in sort of roughly 20 minutes on in-house hardware, which is which has quite large implications for our operational pipeline. So yeah, that's me, and I look forward to the discussion.
Thank you, thank you. Next we have Joel.
Thank you. So hi everyone, my name is Joel Oscarsson. I'm a postdoc fellow at ETH Zurich in Switzerland. So I'm an academic researcher. I don't have a direct connection to a Met Institute, but I've been working for a number of years doing research and developing machine learning weather models. I think in particular focused on the limited area approach then. So maybe just to contrast that with the stretch grid approach that Håvard discussed. So in a limited area model, we would be predicting only a specific region and not this global part, and then have the global forecast from a different model then come in as a forcing throughout the entire forecasting process. And then there's many different ways you can do this. I come a bit more from the machine learning side of things, so you can also, I've been also testing different architectures and approaches to this. I'm also very interested in probabilistic weather forecasting and ensemble modeling, both on the regional and global scale, which is something that maybe we will touch upon throughout this discussion.
Yeah. Thanks very much, Joel. Now we move to Roland.
Yeah, thank you very much, and hello to everyone. Yeah, I'm a mathematician by training, physicist as well. I did both in parallel. And so I've been working on data assimilation a lot, observations and NWP for the last 15 to 20 years, or 20 now. And yeah, I've also been in AI for quite a while, because it was part of before I even went into NWP that I did neural networks and things, but at a time when it was not as mature as it is today. So for me, it's like something coming true, which I've been trying to do 30 years ago, and it couldn't work that time. So yes, and we have teams working on both global AI modeling as well as regional AI modeling at DWD, and Reading is my academic affiliation part. But so we are doing global graph neural networks. That's the Anemoi framework, AICON called, and it's trained on AICON reanalysis, global 13-kilometer AICON. And we also have regional models and regional reanalysis available, so both on the European scale with AICON Dream EU, as well as with on the regional scale, which is AICON D2 Central Europe with 2 kilometers. And so we have been going down the chain with now doing LAMs for Europe, and also it's in preparation for Central Europe. So we just have AICON EU in operations, in technical operations. We call this since this week, actually, 3 days ago, officially, and run this 24/7 on an operational cluster of GPUs. And yes, and it's an exciting thing. It's a LAM, so it's not a traditional LAM in the sense that you had boundary conditions, but we take the full global model as input, which is AICON for us, and then we have a higher resolve 6.5 kilometer over Europe regional AI model running now, and then we would go down the chain further in the coming month, actually. And yeah, so more later, perhaps. Thank you very much.
Thanks, Roland. Now we move to Leila from FMI.
Okay, hello everyone. Also on my behalf, my name is Leila, and I'm from Finnish Meteorological Institute, and I'm working as an AI development manager at FMI. My background is in meteorology, so I've been working around 20 years already at FMI. I started as an operational forecaster, so did forecasts for 10 years before then moving towards the statistical post-processing of operational weather forecasting. And then now I'm leading the AI team here at FMI that develops the regional AI model. And we have pretty much followed the path of Met Norway. So we are also running the stretched grid model that Håvard summarized in the beginning. So running regional AI model in 2.5 kilometer resolution over the Nordic countries. It was kind of a natural choice for us because with Nordic countries, we are also running the regional numerical weather prediction model together, which is used as a training data. So we do close collaboration with Nordic countries also in the AI model developers. And our plan is to put these models into operations. Now we are running them in pre-operational mode, and also it's been quite a steep learning curve also to how to put these models into our operational pipelines, because of course they differ a lot from the traditional models where we are mostly receiving the data and now producing more ourselves. So it's a very interesting times, and it's going to be very nice to be part of this discussion.
Thank you. Now we move to ECMWF and quarantine, please.
Yes, thanks for that. So my name is Corentin Carton. My background is actually aerospace engineer, but I joined ECMWF in 2018, where I started working on the post-processing chain for hydrological forecasts. After that, I moved to the post-processing chain for meteorological forecast, and a few years later, I became the lead of the data processing services team. And one of the responsibilities of our team is the development of Forecast in a Box. So just to describe this project in a few words, Forecast in a Box is an open source project in which the main goal is to package AI weather models with everything you need to produce a forecast with operational quality. And this allows the easy deployment of complete AI-based forecasting systems, taking care of initial condition retrieval, deterministic ensemble model run. You can also compute downstream statistics and generate the final graphical products, which you can visualize interactively in the box. And all of that is designed to be available through a simple desktop application that is easy to deploy. So the project actually started a few years ago, around 3 years ago, as an internal initiative led by our section head, Tiago Quintino, together with GM Hawks, who was previous the team lead. And as AI-based weather modeling became an increasingly important part of the Destination Earth program, the project also received additional funding from Destiny, allowing us really to accelerate the development of the concepts. And it was then truly formalized through our collaboration with Met Norway that we started a couple of years ago on the WMO WIPS project that they do with Malawi. And that project focuses on improving Malawi's forecasting capabilities, and Forecast in a Box is one of the components of that project. That collaboration really has been particularly valuable for us because it gave us a clear goal, and it allowed us to also develop the application around real user needs. So since then, we've been working very closely with Met Norway, the Met Norway team, to build a common solution. We have added the Bris model in the box, together with different flavors of the ECMWF AIFS models. And a major milestone was last year when we did the first deployment of Forecast in a Box, the Forecast in a Box prototype in Malawi, as it was presented at the WMO Congress in October. And today we're developing a new version of Forecast in a Box. We do a complete refactoring based on the feedback we gathered from that initial prototype. So it's a complete redesign, not only of the user interface, but also from the backend. But the concept, we keep the same core philosophy, right? We are also putting a strong emphasis on modularity. And this time we allow users to integrate their own models or their forecast products through a plugin system. But our goal remains the same. So it's really to provide a platform that can run Anemoi models from existing initial conditions, So you can retrieve initial conditions from the AIFS analysis, for instance, of Formula 5. And then it can generate complex forecast products on the fly and provide users with a simple and efficient way to visualize the results. All right. So I know that there may be many questions about the project and its goal, and I will be happy to answer any of those as much as I can. I will not comment too much on the modeling side and the models we put in the box, because I think we have enough people around the table to do that. But yeah, my hope is that these local high-resolution models will keep improving, because they really resonate well with the concept of forecast in a box. And yeah, I'm happy to discuss that further later. Thank you.
Thank you, Corentin. Thank you for the background information on forecast in a box. Now we move to the moderated discussion based on themes. And first direction is that, I mean, as we just heard while the introduction was going on, that there are several pathways different Met agencies have opted towards this regional ML forecasting. For example, the LAM version, where we have the limited area model, and then we have the stretch grid model. And also, what we do not see here is also part of this initiative is like downscaling, super resolution downscaling. And of course, everybody wants that the large scale atmospheric consistency should be combined with the local details for the regional forecasting and decision support. And the question that brings us to this point is that, I mean, how these decisions are made, and how do you decide that, you know, this is the most promising route towards regional ML-based weather forecasting? And yeah, please go ahead, whoever has an opinion.
Perhaps I can offer some first thoughts.
Yeah.
I perhaps to my view on the three approaches is they all have their merits and their framework. So first of all, if you have a stretched grid approach and you go to higher resolution in some area, you could go to higher resolution everywhere, but of course it pushes the number of points explodes rapidly, and so having a nest is of course very attractive. You get high resolution, you get also the communication between low resolution and high resolution. Potentially that's very valuable. That's the question, how strong this is actually in the end. But that's the strength of the approach, that when you cycle it over 6 hours or 3 hours or whatever, you have all scales in the game. If you go to a LAM, you split the problem. You have the global model, and then you have the LAM model with going into the higher modes. You don't have the flow of information back from the high resolution to the large scale, because that's set. But you still have the flow of the initial conditions in high resolution. In contrast, potentially, I mean, you have the same in the stretch grid, of course, but you still have it in the LAM. And by splitting the problem, you gain a lot of efficiency. There might be factor 10 actually or more in terms of training costs and others. Just solving the problems not in a coupled way. Then if you go to last sentence, and if you go to the downscaler, you lose the initial conditions in the high resolution, because otherwise you would be back to LAM. But still, you take everything you know on high resolution, you plug in by giving it the knowledge about orography, about particular effects which happen there. And so it still can be very, very valuable. And it's done for climate science, of course, for many years. So you have a list of things where I don't think you should, I mean, they all have strengths and weaknesses in principle. And it's good to have them all, yeah, and to be able to choose and to deploy them where you think it's beneficial for you and it fits your training capabilities, the computers, the setup, and so this is my initial goal on the three methods.
Thanks, Howard.
Yeah, I didn't want to go first because it's a very neutral opinion, but I think I will sort of second this, that they're quite equal, at least in terms of sort of LAM and stretch grid. We at Met Norway, we're collaborating with RMI and Anemoi. where they're looking at LAM approaches and we're looking at stretch grid approaches, and we have sort of very quite comparable setups. And I think, of course, it's quite hard to boil all these results down to one number, but broadly speaking, they're quite similar in terms of performance. They're also quite similar in terms of training cost and compute, just because really for the stretch grid and for the LAM, the high resolution part is the same, and that actually consumes most of the compute just because the number of edges in the graph for that area is so large compared to the global domain. So I think my feeling is that whoever sort of works the most on their setup and pushes it the furthest will probably get to the best setup. And I think it's also interesting to investigate these setups in parallel, because I think we learn from each other, right? So sort of the only real distinction is that for the LAM you rely on an upstream global forecast. Yeah, I would.
Thanks. Joel, you wanted to say?
I can just sort of chime in here, I guess. Maybe it's a boring starting point saying, oh, these are actually all pretty good. But I think I largely agree. It's not, maybe when sort of people started initially developing these, there was a bit of a question, okay, is one of these just the superior approach? But I think we've sort of all found at this point that, well, you can actually get all of these working quite well. It's really how you want to integrate them in existing operational pipelines, and what data do you expect to have available to you, and what kind of flexibilities do you want to have or not. So as Håvard nicely said, I mean, the LAM approach has this dependence to a global model. That's a sort of means that you need to run a global model somewhere, but it also gives you the flexibility of swapping out which different global model you're running. The stretch grid approach gives you the global forecast from just running one model. That's great. Maybe something I like to highlight, because I think it's nice that we also mentioned downscaling here as another approach. And one quite exciting thing, I think, is when we start to see these, like the limits between these blend a bit. So Roland mentioned this already with the LAM approach with the AICON, that, okay, for a machine learning LAM, we don't just need to have boundary conditions, but we can actually have these also covering the LAM area, which means that we're going both from an initial condition and from the coarse resolution field over the actual area, and we just let the model sort of combine these in some way, which is one of the hybrid LAM downscaling approach, if you'd like. And you can start kind of thinking even past that. Okay, what other sources of information could we include to the model here?
Anyone else? Otherwise, I mean,
I will quickly comment, because I'm more on the operational side of things, and definitely I think the different configurations in these models is also important. The way it's trained and the way it's used operationally will have an impact. As you said, like depending, for instance, of an external global model to run your LAM may be an issue, or maybe it may be actually an advantage, right? While the stretch grid will provide everything packaged already. So in a sense, it's much easier to integrate into your workflow, because you get the whole thing already kind of running. I mean, these are different things, right? So I agree. If you manage to package it nicely into your model, it may not be a difference, but I think in terms of data retrieval and external dependencies, the models have different approaches. So for instance, in our concept of the forecast in the box, the stretch grid model works really well, because we can just deploy it just for initial condition, and then we can also move it around. We can move the graph to different locations. Actually, a question that I have for you: can you do the same with the LAM model? So can you easily move the domain from one location to the other?
Joel, who wants to?
Okay,
Yes,
go ahead.
there's no principal difference. Yeah, it's
Okay.
of course a question of how you trained it and how well it does it, but
No, yes, of course. There's the whole like scientific validity of that moving the high resolution array, of course.
like can I make one comment? I mean, yes, if you have a completely different global model, then you have to work on the interface. It's clear. But if you have, let's say, the same, I mean, for example, we have AICON global, AICON EU. It's basically a nameless difference. Of course, there's also all the coefficients you pull, but in principle, these work on the same type of grids. It can pass the information in memory to the LUM, and it's fine. Yeah, so it's kind of, yes, I agree. It can be a topic. It can even be very tricky for the following reason, for example, which we should touch as well. There are models trained on pressure levels, and there are models trained on height coordinates, which makes quite some difference. If you have only few levels, like 13, what was the first version of the global models, it makes a big difference whether because the interpolation becomes kind of non-perfect. And that makes a big difference. We have tested like verification, and I just wanted to put that in, that there are differences in the way it's done, and it's yeah. And then of course, if you plug these models into each other, that might cause issues actually. Or I would expect that it does.
Okay. Maybe a final, like, before we move to the next theme, I mean, if we think about seamless transition between the boundary conditions, and so, for example, if we have a LAM, and I think somebody mentioned that if we use a different model data output on the boundary condition, then it will fit seamlessly. But is it really the case, or then there will be different fine tuning needed for this regional model if the boundary conditions are changing? Or then, I mean, ultimately the point is, auto-regressively, when we are moving forward, which of them better suits such kind of the seamless transition in lead time?
I can share some experience here maybe. So when you maybe starting with the point of you swap out boundary conditions, that requires fine tuning, and I think in general fine tuning in those scenarios for limited area models helps, but you can I mean, they work without it, but you can get improvements from doing so. For the seamless transitions, I guess there's a question here if seamless transition is always what you want. Do you want an accurate forecast, or do you want a seamless transition, and are these perfectly aligned? Because often I think we train models to match like a regional analysis or regional reanalysis, and it seems that to sort of achieve that, to do that matching as good as possible, often that means that you will not get the nicest seamless transition.
I see your point. Depending on the objective task, the models has its own priorities. Anyone else on this, or we?
I would say there are open questions as well. I mean, it's
sure.
Some of the things. Yeah, we have tested some things. We are trying to move things to operations. We might discuss it further, but of course there are hundreds of unanswered questions I would have on this, and it's literally 100, because you can start to ask various things, and it applies to the models themselves, how they are trained, what they are doing, when, at the boundary conditions, in the long run, etc., etc. Yeah. Also, this phenomena of lower resolution versus higher resolution, and what it does, and what's the dynamics you really see. You have also mentioned in your introduction already the temporal question, which is another question. How much of the dynamics you can down interpolate, if you want, in this terminology now used, and how much you would need to cycle to get phenomena in it. Can you top down see the phenomena? Can you evolve them by cycling from initial conditions? How much? What's going on? How? I would have a lot of questions which I haven't seen answered yet.
So if I just ask this question, like as a priority for the next few years, would it be like better regional coupling or better treatment of extremes? What would you say? You know, like if you have to prioritize, then like just an open question. It's just asking out. Open, yeah. Yes, these are all open questions. I agree. I mean, but just for priority's sake.
I mean, maybe I can't really choose between the two you listed, but I think what we're mainly working on now for Bris is we're trying to improve the spatial consistency, which has to do with this CRPS-based loss function. And then we're also trying to increase the spread in the model, because we can see that it's slightly overconfident. And that also has to do with the way it's trained. So I think at the moment, those are sort of the two top priorities for us.
Leila, please go ahead.
Okay, if this will support that, we can kind of wish anything. So one thing that we would definitely need is to incorporate more parameters. The parameter set is rather limited that we currently provide. For example, considering the aviation, there's not much for them to actually use in the AI models currently. So we are also at FMI researching different ways to incorporate new parameters that are not into the base model yet, but somehow incorporate them in the regional models also.
Okay, I forgot. It was somebody raised the hand. Sorry, I forgot. Please go ahead. No? Okay. Then I think we move to the training and scaling the training data set and the scaling of these models. And of course, how you decide which, as we were discussing, like, you know, given the operational nature of operational requirement, it could have an effect on your decision. And therefore, I mean, we will touch upon the bottlenecks, for example, the training data quality or the computation cost, or as briefly mentioned, the temporal resolution of these forecasts. And the question is, if we talk about the barriers to training at such high resolution, what are the main barriers in training such models? Howard?
I think one large barrier that a lot of institutes will meet is that their sort of regional data set is significantly shorter in length compared to ERA 5. And I think most results so far indicate that having a really long reanalysis data set has a big impact on the model. And so we have some ways to overcome this by sort of pre-training on only ERA 5 with very coarse resolution, and then gradually introducing the high resolution data. But I do still think that having a 40-year long regional analysis would lead to a better a better model in the end. So yeah, that's one of the challenges.
Sure. Joel?
Yeah, I agree that I think the having high quality for a long time data set is probably one of the main hurdles here for these techniques to really be adapted. And I mean, the transfer learning approaches that you've been doing in Bris, for example, is one way to get around it. And I think the general foundation model trend is also something that I think will start to play a role here. And I think it's a little bit surprising that we have seen quite little of sort of Earth system foundation models of different kinds really adapted to these regional settings. That's, I think, one area that's very underexplored, really. But I mean, there's lots of ongoing interesting work in that direction. But that's maybe one way to kind of get past that barrier as well, to really have something that is very easy to do the transfer learning from.
Roland?
Yeah, I think we had slightly better experiences with shorter periods. I mean, I've just had a discussion with our main people training AICON EU, and we have 15 years of data for that, but even after 6 years of training, we get a reasonable quality. It's not as good as 15, and I would expect going down. So I agree that the more the better, but still we were able to get a reasonable quality forecasting system with even 6 years of data on that scale. That was my first remark. So I would hope that even in the future we can use this more efficiently, even if we have shorter time. So there was one, but also we do transfer learning. One has to say we have this AICON grid and as a natural grid, and we go from 52 to half the resolution, double the resolution each step, and then we go down, and that works pretty well actually. It was astonishingly well. And yeah, perhaps I have another thought on this high resolution. I mean, it was also asked here. We will come to questions later, but I saw one. I mean, we are all trying to go down the resolution, and there is now data sets in Destiny on 500 meter or 750. We have AICON D05, that's 500 meters in operations, in technical operations for 1.5 years now, and we have data sets lying around. And of course, I think these direct observation training techniques, which you can do in different ways, it's not our main topic, but they also allow you to go down in resolution because you learn the behavior of fields depending on input parameters like location but also further parameters, not only location. Location alone would not be sufficient. So there are a lot of possibilities to get into resolution below the reanalysis actually as well. And so I would expect that there's a lot of potential which we haven't seen yet in the whole field and in this whole framework.
I was wondering, I had this thought when I was preparing, is there any, so for example, when we train it on the like AIFS or AICON model trained on the global graded data, and then when we fine tune it on analysis, so then we see a shift in the model and it needs some time to fine tune on it. Do you see the same behavior here also when you are testing on operational analysis while it is trained on reanalysis? What's your observation on this?
I mean, we haven't seen it that much, I would say, because our reanalysis is pretty new. So it's basically the same model. And we have seen differences by changing some of the parameter sets. We made some mistakes initially. So we had the wrong parameter set in the first parallel routine, and were looking for reasons of artifacts. It makes a difference what you change and how you put it in. So there is kind of sensitivities of the models to data, which are much stronger than one would expect, and they really matter. So I also heard from other colleagues that they tried to use one model with another initial condition, and that didn't work that well. So if the model, the reanalysis fits the initial conditions, it was much better than taking the same very good model trained well, but taking another initial condition, and then it wouldn't do a very good job. So I think there are a lot of sensitivities in the whole game, which we just learn now step by step. Yeah.
And has an opinion, or I can shift to a bit. So since we are talking about training, and I would like to briefly touch upon the probabilistic training scheme, which, I mean, we saw recently that the paper was out in arXiv based on CRPS training. And where do we see the most of the improvements? So of course, we know that sharpness or like getting the extremes well represented is what we expect. But I was wondering in which of the variables, if we opt for, in the regional domain, opt for CRPS-based training, where do we see the most of the improvements? Yeah, Hobart?
In our case, it's for sure precipitation. Just because in the deterministic model, it often just ignores convection completely. And you're also not really able to tell the difference between a large-scale system and a system of sort of smaller cells of convection, just because in the smooth forecast they look exactly the same. So yeah, this is definitely the main the main variable.
Now I guess. Oh, sorry, Joel. Yes, please.
I can maybe just chime in that I think like all of these fields that have a lot of uncertainty, because this is really what you're losing with the deterministic models, right? You're smoothing out this uncertainty. And the switch to a CRPS training isn't just a switch of training objective, it's inherently reframing the problem to actually produce samples from the distribution. So a lot of I guess you will, for high resolution fields, you can think of it as these fine scaled features that you have quite low predictability over. So to then actually model the uncertainty that we know is there is where you actually gain the most.
Cool, thanks. Anyone else? Okay. Next we move to the verification and the trust part of our discussion, and also a bit on the operational integration. So of course, we have seen that these models are able to produce skillful forecasts, but if we talk about operational mode, it depends how to trust them and where they fail, and how it could be integrated into existing warning workflows. It is especially important at this scale of regional forecasting because we are not talking about average forecasting skill, but it is about, as I said briefly before, the local extremes, the uncertainty, if we can get it right. And yeah, so therefore the question is, how should these regional ML-based forecasts be verified, trusted, and integrated into operational forecasting workflows? What's your experience? Yeah, basically. Yeah, Leila, please.
Yeah, at least I can share what was our approach. So before we started to run our own AI model that we have trained, we started to run the global Bang weather, which was the first one one of the first that was releasing the weights just to get experience of how to run these models and how they look like. And we very early stages actually incorporated into our operational workflow. So already provided the data to our forecasters and to our verification system to monitor it along different model producers. Just, we were kind of treating it as another model amongst the others, no matter how it was produced. And that's what we have also done with the regional models. So we are running Bris, we're running our own IL model in-house, and yeah, I know it's a bit risky to provide the data very early on to the forecasters because there are still things that we change. And if there's something happening in the production that causes weird values, then the forecasters may lose the trust to the model. But we have done a lot of training. We just had like 2-day training for our operational forecasters about AI weather models and so on. So I think we need a lot of discussion back and forth with the forecasters, and of course many of our verification is done against points, of course, which is not enough. So we need to provide the actual forecast to the operational forecasters and also get the feedback back from them to kind of develop these models together.
Oh, thanks. Yeah. Sorry. Oh, there was a chat box. Howard. Yeah.
I think we have a fairly similar story, but just running the forecast pre-operationally and sort of looking at it every day is helpful for this. And then of course we get some extreme cases every now and then we can sort of easily compare them real time side by side to the current product and try to identify weaknesses from that. But I think you need a combination of everything, right? You need. overall
Yeah,
scores, and you need to collaborate with the forecaster or the duty forecasters. So yeah, I would say introduce it gradually. That's our...
Yeah, I mean, let me pick your mind a little bit. So, I mean, as you said that, we introduce it to the forecasters, or, I mean, so I was wondering, these regional ML forecasts, are they able to represent the events that matter the most for operational warnings? Or when you see that, there is a weakness, what kind of weakness it is? If you can just express it, like say a bit on that.
Sadly, I don't think I have the answer to that. I mean, like for instance, we see that it underestimates extremes for precipitation, but we can easily explain that via the training data. So it's not necessarily linked directly with the method or the model. So you quite quickly get into very sort of detailed and complicated issues, but at least sort of running it and looking at it reveals these issues, and then you can sort of work on them step by step. But it's I think it's hard for me to now sort of list.
Okay. Okay. Then I was wondering, based on Leila's comment, that I mean, then what would convince an operational forecaster to rely on your product that you are putting out in front of them? Of course, I know that's a generic question, but I mean, overall, when it leads to such a it takes years in operational mode. So, yeah, Roland, please.
Yeah, I mean, we have gone the same way. I think we are all on this track as the weather services, that we put AI models into operational frameworks, and our forecasters get a chance to use them or to compare them. So what we have done for the global AICON for a longer period, more than half a year, is more or less daily, bi-daily reflections of forecasters looking at the model in contrast to other AI models like AIFS and also to the classical model. So kind of having all of them available and saying, this is more plausible, this is more plausible. So we collected cases. This is, of course, not a statistics. It's single cases where the forecaster says, here it was crappy and here it was really good. That would have helped us a lot. And so we have a record of some of these cases where they say, yes, snow, is it snow or is it water? Is it icy on the road? Is it not? These are situations where they really struggle, because if they tell everyone it's icy and it's not, they lose trust the other way around. And so here we have some cases where the AI model was, and even the scores and these type of things didn't correlate necessarily. So we had models with better scores, but less realism in some of these cases where the forecasters had more trust in the model which did this right than in the model which had the better scores after 5 days. And yeah, because it was smoother, it was slightly a different resolution, and so gaining trust comes from having good experiences and having a stable forecast over a long period. When I was myself looking at our model, when you had this high precipitation over Portugal, over days, yeah, there was this weather coming and raining, and half of the country drained. And I was looking daily at these forecasts of AI and the classical model, and it was so good. And it definitely had never seen these high precipitation events before. And it still was able to generate them after 4 days in the forecast, after 3 days, after 2 days, it was better. It was a little bit less high than in the classical model. So kind of it was slightly damp, not much, but but it was still very good. And it was convincing, yeah, because it was really a case which mattered and where the model did a good job. So I think this is how it will go, because if you have a model which is fast and good, and you try it out and it provides good information when it matters, they will use it.
Thank you very much, Roland. Now we move to our last theme of today's panel discussion, which is on forecast in a box, its deployment. as well as its local usefulness. And of course, as briefly mentioned by Corentin, that it is an idea because AI forecasting system here is lighter and faster than the traditional numerical weather prediction system, and the deployment is closer to where the forecasts is consumed. But the question is whether such system can provide useful, trusted, and maintainable workflows actually, especially at that scale, at that local scale. And therefore, the question that I have drafted is that can forecast-in-a-box approach make regional forecasting more accessible, portable, as well as locally useful?
Yeah, I can try to give some hints on that. I think it can definitely help because we've seen that those models are much simpler to package and to run, right? So that for us was kind of the game changer. And also, as we're going towards high resolution, we will quickly see that the typical workflow that we have to compute post-processing will quickly be the bottleneck of the entire system because these models will run in minutes, right? Maximum will be 10, 20 minutes, even for the high resolution that we have now, while the product generation can now be 1 hour or 2. So trying to combine these two steps, running the model and the post-processing, will already give you kind of will allow you to reach higher resolutions. That's the first point. In terms of localized forecast, about the validity of those, I cannot really comment on those because that's more on the modeling side. I think it's a very nice feature that the LAM or the stretch grid models, you can move the graph in different areas, and that works for me really well with the box because that means you can deploy like a theoretically infinite number of forecasts in different places, right? And the box, forecasting the box allows you to do that very easily because it's a simple application that you can install on a virtual machine or on a laptop if it's a small model that you want to test. But you can also deploy it on an HPC if you want to run a very high resolution ensemble. I think that works really well. It is linked with the Anemoi project, so we are also trying to keep up with the pace of development of these models. Every day there is a new model coming. People are working also on temporal and spatial downscaling, working on training directly from observations, and we are working closely with the people developing those models so that the application will allow you to quickly switch to the new model. If there is a new model with additional benefits, it will quickly be available in the box and it will run. So you will be able to transition from your model to the new one. I think that's where the box is interesting. If it proves that you can move the localized high resolution model, it can be applied to then many projects. You can package your model and give it to your European or even international partners, as we do with Norway and Malawi. I think that's a perfect application that can help low-income countries to get more sovereignty and they can run their own forecasts. But you could also apply it to the private sector as well. Private sector could then run their own localized forecast and compute only the products that they're interested in, and that could be applied to a lot of different sectors: energy, finance, climate, and you name them, right? So yeah, I think there are many. I think it's a good opportunity, these models, to also improve not only the modeling but rethink a bit about how we build the whole computational chain instead, in a sense, for the forecasting. Yeah.
And I was thinking about the data sovereignty part and thinking about data sparse regions, where we do not have synopse stations or long-term observations, but we have. I was just thinking out of the box that we have telephones. And telephone, like your mobile phone, and your mobile phone also represents proxy representation of temperature, local scale temperature or humidity. And I was wondering, as part of this whole initiative in future, do we expect to fuse this kind of proxy data in your pipeline, especially in the data sparse regions? How do you see that?
Yeah, it's a question that a lot of users are asking every time. In Forecast in the Box, we haven't tackled this yet. I think as soon as we have a model ready to run on local observations, we will definitely tackle this first, because it is really something that people are asking for. What we could leverage now is use local data to do local verifications. I think that would be a quick win, and that's something we could integrate in the future. But to improve really on the forecasting side, that would be more on the modeling side, or to also leverage some, post-processing capabilities as well. That is something we could do.
Okay. Thank you. Thank you, Valentin. Anybody else? Or I would say we can move to audience questions, if that's all right. Okay, so we have a question. How do you model given that we don't have a high resolution ops, especially in complex terrain? Yeah, Howard.
So we mainly verify against synoptic, so surface stations, and of course these are randomly, I guess, placed in the terrain. So you, on average, I think you can deduce something like you sort of integrate out this effect to some extent, and then we also look at sort of spectrums, or the Fourier transform, to see if the spectral properties match that of the NWP model. So I think those will be two examples of
Roland?
Yeah, I also would say we have a lot of high resolution data. And I mean, NetAtmo stations, 50,000 of them, 10-minute data from Synops, radar data at 250-meter resolution, satellite data at, the new generations coming, or is kilometer scale. And so they have now the next generation now 2.5 minutes rapid scan. Partly, we are discussing what's next, what's needed for UMETSAT and the satellite generation coming. But if we could use all of this, we would be so happy. And it's just a lot of work to data cure and to actually process them. But I think it's not the problem that we would not have a lot of data. Of course, on base surface stations in the mountains, that might be a little bit less well covered. That I would agree. And then, but yeah.
Okay, thanks. Then from Conrad, we have which approach, and the stretch grid or the LAM appears more robust for rare extremes that are poorly represented in the training data.
Joel, do you want to tackle? I mean, maybe I can start by saying that the LAM models being trained in Anemoi are not yet probabilistic. So then I think it's hard to compare extremes between a deterministic LAM model and a probabilistic stretch grid model. So I don't think I don't have a basis to make this comparison.
I think also the question is not about LAM versus stretch grid. It's whether you have a probabilistic model that actually represents a distribution that can capture extremes, or a purely deterministic model. And I think you can build such with both approaches.
Yes, sure, please go ahead.
As a mathematician, perhaps one remark. I tend to look at things from a kind of algorithmic point of view. And I would say, if you look into if you have graph networks, let's say, a transformer is a different story perhaps, but if you have graph networks and you train them globally, that might have there are benefits in both, I want to say. If you train them globally, you might pick up extremes from regions which are outside of your local domain and still benefits the local domain. So there would be an argument for having a kind of stretched grid approach. On the other hand, it's always a question of the capability of the model. How many parameters do you have? How well do you capture the whole variability? And if you go to LAMs, and that might be actually an advantage for the LUM because you don't have to train it and adapt it everywhere. So I'm not sure. I wanted to say I see arguments from the algorithm for A or B, which could pay out depending on your configuration. And I wouldn't be surprised if someone comes up with a comparison and says A is better than B for extremes, and another one does a different setup, different resolution, and comes up with a contrary opinion or result, even hard experimental scientific result, because it depends so much on how you configure and how you do this. Yeah, and
thank you, Roland. And then Gisli Bjorn asks, most global models are trained using pressure levels and some surface level fields. For a LAMP setting, might it be more relevant to use model levels, example hybrid sigma pressure, directly, especially in complex terrain where vertical resolution is important? Interesting question. Who has complex terrain in his?
Yeah, we actually, I'm biased, yeah, because we have the terrain following local regional model, and we see that this has advantages because the pressure levels might cause some problems sometimes, but it's biased viewpoint. I had some discussions where people said LAM is better here, but I'm not sure. I haven't thought it to the end, so I don't want to be taken too serious with that. No.
And we have a final question on yeah. So as Leila was saying that, we have we are interested in aviation, or somebody says, we have a more agriculture oriented, we are the variables that are more important for agriculture or for aviation, but the question is asking rather a one size fit all or to target, user specific regional variables per se being part of this workflow. What would be your opinion? Yeah, Howard?
I mean, I think we now quickly get towards sort of more weather generator type models, but I mean, in principle, you can do similar things with the stretch grid or LAM, I guess, where you sort of fine tune these separate decoders that you can train to predict a very specific variable or a specific subset of variables. And I think that works sort of reasonably just because these models are so fast to run, but probably something like the weather generator that's sort of trained to do this specifically will work out better in the end, I would sort of guess, yeah.
Oh, I think question 2 was skipped. Oh, sorry. Yeah, sorry about that. In NWP models like VERF, we have stationary data like LULC, DEM, etc. How it can be represented in AI regional models? Does it really need it? Anybody having an opinion on this? So again, I can repeat. It's the question 2. In NWP models like WRF, the weather research forecasting model, we have stationary data like LULC and DEM, which is digital elevation model, something I think. And how can it be represented in the AI regional models? Does it really need it? Well, anybody has tried it?
I'm not sure that we are using, of course, orography masks and various input data, and I think everyone is.
Yeah.
So
Yeah.
I don't understand the question fully because you put in a lot of fields into your models. It's pretty simple usually because they are made if you have it on the same grid or even not on the same grid, depending on the way you've coded. You can just add any information to it anytime and see how much information content is in it on top of what you have in already. So in this sense, is it needed? Yes, the more, if it fills a gap, it might be beneficial. So.
there is one last question. I think there is some time still, and it is about, so from training a model on a given specific regional climate, and then we apply it on a different climate. And what's the panel's opinions on transferring these kind of models to a different climatic zone, climatic regime? Yeah. And has anyone tried it? I think I saw in Meteor Swiss presentation, in last year, I saw this kind of presentation where they trained on the Nordic region, and then they were checking in the Swiss Alps and some region in Germany. And it was still preliminary result, but I do not remember enough. But I don't know if anybody is tracking that or has their own opinion.
Yeah, I mean, those are quite old results, and this was for the determinant. So it's a very old version of the model. But I think one thing we saw in that specific case was that the model didn't understand the tree line at all in the Swiss Alps, just because it's so different than in the Norwegian mountains. So you have, I think with this you do run into these problems that the model learns something about the specific region you train it on. But I also think that this can be overcome by introducing sort of more specific descriptors. I mean, you could have a variable, right, that describes the vegetation coverage. There is also ongoing work now on training these sort of stretch grid models where you move the high resolution area. Sort of every batch in the training, you train on a different. So I think this is a very open question at the moment, but it's definitely something that's being researched, and I'm sure will improve in the coming year. Yeah.
Thank you. I think we can, I mean, I would say thank you everyone for sharing your opinion, and thank you to the audience for asking these questions. And ultimately, if we look at today's discussion, I mean, what we realize is that there is enormous freedom in the choice of how we drive such a model. And of course, some of the choices are genuinely new. And as Roland said, hundreds of unanswered questions, and which one to focus on is currently open. Of course, we opt for different training choices, and in that way, we push the research community to get answers. And definitely, we have not conversed yet. Maybe in some years to come, we will have a good answer on this. Or of course, that depends on what we exactly want from the model, given our area-specific requirements, such as whether you want a seamless transition, or or I want my model to perform good on the precipitation variable. And especially on the training data set, also we were discussing okay, as long as extended the data, the more the data is, that is good. But then I think Roland pointed it out that it already started matching the scores on 6 years of data set. So, and there is strong sensitivity to the data on which it is initially trained. And if we change to something else, then the weights that the model has learned and the sensitivity that is there and the variables that you have chosen we are still figuring it out. And and about the Forecasting the Box initiative, what Quarantine was saying is that yes, we can reach such a high resolution nowadays, especially with approaches such as current collaboration with Norway and Malawi, with the SGM approach. And of course, it is hard to also maintain your repo with the everyday new coming models. And of course, these kind of approaches or the efforts will lead to democratization of models which are used in forecasts, and especially rethinking how we make the workflow more modular so that it is adaptable to different requirements. I think that's overall summarizes our today's discussion. And thank you, everyone. Thank you very much. And thank you for your contribution. Sorry.